Okay, super. Happy to give you a pretty short talk here on the role of trusted hardware and what it plays in consensus. Here's the compressed meme version of all the content of my talk. I think that there are I'll give the background on trusted hardware in a second. If you already know about trusted hardware, then the first couple of applications to consensus maybe are the obvious ones, or you've already seen something about that. You can like automatically use trusted hardware to make your crash fault or message omission fault tolerant protocol more secure. You can use trusted hardware to substitute for zero knowledge proofs. Talk a little bit more about that. But really the point that I want to make that I think are more interesting points that are takeaways for you in the consensus world is that trusted hardware can do something that other protocols don't, which is preventing against long range attacks. That can be really important when you in turn use consensus for control plane for private computation. This takes on an even more important meaning. And there's a dimension of the use of trusted hardware that I think is really underrated, which is essentially being able to prevent hard forks and changes to consensus protocols, especially ones that involve user privacy. So those will be the new points that I want to make. So I don't want to assume that you've heard of trusted hardware, so I'll give a short, high-level intro to the concept of this. So trusted hardware, the way that I'm using it, there are some other simpler versions, but the kinds that I'm most interested in are what you find in processors like AMD SEV compatible processors and Intel's SGX compatible processors. Arguably, the definition of T also includes like the secure key manager elements that you have in every mobile phone. But mostly I'm interested in the ones like SGX. These aren't separate pieces of hardware. It's really just a feature that's present on many, but not all of, say, server class Intel chips from the last, 5 years or so. Half of them will already support this. So it's a feature in existing processors. And the basic idea is that it provides isolation and it provides remote attestation. So the isolation is basically the processor is secure when it leaves the factory. Even if you own the chip, if you run a program on it in this isolated mode, then even you have root access to the machine or even physical access to it. You can't go and look at the contents of the program while it's running. This is like ring -1, like it's more secure than root. So it's isolated even so someone with root access can't look at it while it's running. So you can't tamper with it and you can't eavesdrop on it while it's running. The other thing that's depicted here is remote attestation. So when the hardware leaves the Intel chip, they have imbued it with a private key that allows it to sign these certificates, basically a signature on the output that it produces. That's traceable all the way up to Intel's published public key, that you find in certificate repository PKIs. And so if you see this signed signature from the trusted hardware that says this is the program that produced this output, you know that you're interacting with an authentic device. So what this enables you to do is disintermediate developers and the owners of cloud accounts. Developers can publish their code on GitHub. Users can look at they can compile the code themselves, check that the certificate that's signed by the trusted hardware matches the program that they were expecting. And now they can trust that the output that they're looking at actually came from the software that they're claiming. You don't have to trust the developers. You don't have to trust the operator of the account. And then you can decide, okay, I'm going to interact with this program. I will, start a session with it, do some secure data. It's roughly the way that it's used. Maybe the other way, how do you use this for a consensus protocol? Well, if you have a consensus network, you can just add TEs, and now they all are running this secure isolation mode. This provides some benefits. I'm going to talk about what those are. The first thing is that what the TE can do is it can provide anti-equivocation for you. So you know that in BFT protocols, you have to worry about what happens if the leader is sending one message to all the, half the nodes and a different message to the other half of the nodes. But the trusted hardware has, a monotonicity to it. You can have counters that once you write them once, you can never go back to the prior state. You'd have to restart the program and re-register in an entirely different session. I see you going waving the hands there. Okay, but I think that you have in mind sealed files. There are ways that you can even more. All right, no further. I have a whole page of caveats in all of this. I have a page on caveats because I'm just saying, if the TEEs give you the guarantees that they claim to, then I will talk about all of the interesting consequences of this enriched model where you have this trusted hardware. Whether or not any of the hardware actually does what I'm claiming, that it can do, that's a whole separate topic. But, this is meant to surprise you about what are the consequences of the strong trusted hardware model if you have it. So because you can use this trusted hardware as a way of blocking equivocation at the consensus protocol, then you can use a cheaper consensus protocol because you're getting anti-equivocation from the hardware rather than from the replication. So this allows you to simplify, you can use a cheap consensus protocol in place of a proper BFT protocol. Anywhere that you find zero knowledge proofs for validation in consensus, if nothing else, you can use trusted hardware as a substitute for the zero knowledge proof. So again, the caveats apply, right? It's different fault model and assumptions. We can talk about that with any remaining time. But the functionality they provide is similar to zero knowledge proofs. So you could use these as a substitute. So if you already see a place where you could use zero knowledge proofs in your consensus protocol, you could use trusted hardware as an alternative to that. So we see this already used in places like builders. So there's lots of trust minimized builders that use trusted hardware to show that they're following some, order flow policy. There are no rollups that use trusted hardware either as an alternative to zero knowledge proofs or as just in conjunction with zero knowledge proofs for the defense in depth. So these are, I think, the well understood applications of trusted hardware, but I want to point out a couple of more, surprising consequences. So this is one that I think is the most important. So long range attacks in consensus, right? This happens when, right, you have a proof of stake system, there's some quorum of nodes at the beginning, blocks progress, the quorum changes, right? Everyone had keys that they use for signing. And unless you rely on weak subjectivity or you just assume that everyone agrees on a checkpoint that's not too far back, you're supposed to go look from the genesis block and validate everything going forward. The concern is that even the people that were alive in the quorum early on, their keys are still relevant in some way, because someone who is trying to look at these signed evidence as what happened, from Genesis, they can still be fooled and start seeing like a private alternative fork, right? You could fool them. The thing that makes these long range attacks, what's long range compared to short range? It's relative, but relative to what? It's usually relevant to the bonding time, right? Because if you are requiring some staked collateral from these guys, if you hold on to that locked forever, then maybe this is fine. But no one wants their stake locked forever, right? If they're no longer active, they eventually want to be able to withdraw their deposits. As soon as they can withdraw their deposits, their keys would still be relevant for fooling someone if you give them that fake block from, Genesis. But now they can't be punished anymore because they've already moved on with their funds and stolen off, right? That's what makes this a long range attack. Well, right, so what's the answer here? Well, this quality of trusted hardware that they can provide non-volatile counters, right, means that you can have it so that you output a signature, but only after you've deleted the key or at least marked it as inaccessible again. So now if you try to go back and now reuse this, your key's unavailable, you can't get the trusted hardware to do this for you. So this can be a defense against long range attacks, even when nothing in your consensus protocol can do this, or if you release, stake after some time, then you might still rely on the trusted hardware as an alternative. The problem that I have been caring about the most recently is the idea of confidential computing on shared global private state, for which multi-party computation of some kind is the leading alternative to trusted hardware. And so this is where you have some private data, but the private data is secret shared among some quorum of nodes. Problem is that you have to trust this quorum of nodes not to decrypt the inputs and intermediate values as well. There's some notion that there's some output that they can compute if they follow the protocol. They're only supposed to compute that program, but nothing cryptographically stops them from colluding and decrypting everything, the inputs and the intermediate values as well. So this is the collusion problem in multi-party computation. I think this is a big deal for which there's really no other good alternative to stop it. So what you can do with trusted hardware is have trusted hardware required for these MPC nodes that hold shares of the decryption keys or of the MPC keys. And so now these will be in a mode that is following a blockchain. All right, and so now they will only, it's not a matter of having to trust them not to collude. You still have several nodes, each of them only has a share of the data, so they all have to work together to do anything, good or bad. But they aren't, it's not like they just have a choice of decrypting all of the inputs. Their trusted hardware prevents them from doing anything except running the MPC algorithm that is the one that's committed to running and authorized to run typically according to a blockchain. Now I say this blockchain mode here because That's kind of the most convenient way to act as like a control plane and a commitment, so like, here's all the bids that have been collected in an auction. Now we're going to call time, no further bids. Now we're going to run the MPC on all of these bids that have been collected. Multi-party or a blockchain is a good thing for that. That issue of a private fork, though, is now a big problem because now it's kind of like saying, well, now the MPC nodes aren't the problem, but we're relying on the blockchain for the view of what is the correct session to run. So ideally, even the blockchain nodes there would still benefit from running, the multi-party computation. I guess the distinction that I'm getting at here is that, back to this issue of like long-range attacks. Well, one of the things about long-range attacks is, at least in consensus, you can eventually tell that there was this attack. If it's a double spend, you at least, detect it and know about this afterward. Even if it's still damaging, you at least find out about it. The insidious thing about things where a private fork could be used, like you don't have to publish the private fork to get the damage. If you use this private fork to tell the TE nodes to reconstruct data that they weren't supposed to, that doesn't necessarily leave evidence. It's like a privacy failure rather than a, integrity or visible side effect failure. So even in this setting, it probably benefits from being able to have an extra defense against these private forks existing, let alone, being visible and where you could slash against them. All right, so that's the point there about TE and collusion risk. There's, I think, a really underrated protocol called Puffer Finance. So I like to talk about this. I try to get snippets that explain it this way from their website, but it's mostly other things. So this is as best as I understand it, and I have nothing to do with Puffer Finance. So I just like to advocate this on, core idea. You've maybe heard of delegated staking or liquid staking providers. These introduce a counterparty risk. So the idea is that you're a validator, but you don't want to do the work yourself. So you delegate your signing authority to some staking provider. Now the staking provider could misbehave, and if they misbehave, then you get slashed. Your principal gets slashed because of the misbehavior of this guy you delegated to. All right. So what can you do? Well, you can add the trusted hardware to it that prevents the staking provider from doing anything that could be slashable. And so now you get to look at their remote attestation, check that it's running non-slashable code, and then you only delegate to that instance of non-slashable code, not just to the provider to do whatever they want with, hopefully not get you slashed. You get this, affirmative evidence from before you give them the delegation that imposes a constraint on them that they can't do anything slashable. This is cool because it's not even enshrined. It's not saying you need to modify the protocol to do it. This is just like sidecar. You just can get, the staking providers one at a time can be convinced to do this because that's providing value to their, delegation customers. Okay, let me get to the last topic that I think is really underrated, which is the use of trusted hardware to prevent privacy rugging or changing the rules out from under users who have some expectations. So, cover this concept of remote attestation. I wasn't super clear, explicit about it, but maybe you got the idea. You're delegating sensitive data to a particular program because that little remote attestation certificate you get has the hash of the program binary, as part of the, data signed in the certificate. So you say, I'm going to trust my sensitive data to this particular enclave program. That's the only program that gets to access it. That's great, but it's really rigid. So the problem is that every software, people want to update software, there's bugs, you need to patch the bugs, people add new functionality, they want to incorporate that too. So you want to deploy your sensitive data, but now what happens if someone, you want to change it? Do you then have to just go redeploy your data? What about users who went away? Like, is their data washed when you upgrade the program? You'd like to be able to upgrade the program sometimes and take the existing data along with it. So the next approach that people do for these is really problematic. It's based on code signing. So you can say, instead of delegating to this particular enclave program, I'm going to delegate to any program that's signed by the app developer's key. Right? So now the app developer is in charge and can deploy other programs. All right. This obviously isn't good. This is just relying on the app developers, right? You might as well just send them the data and say, please don't, misuse it, right? Because you don't get any guarantee. Okay, so this is a bad solution. The next best thing you can say is, I want to trust my sensitive data to any enclave program that's authorized by a DAO. So this is pretty good because now you're referencing this blockchain. a DAO would have to do some, multi-sig to approve this. And additionally, you can have like a notice period. So you can say that just like the standard practice for upgrades and smart contracts, there's a pending period so everyone can see and, argue about it before it, takes some place. So this is good. You can say the devs, but only a majority vote of this DAO, plus the software devs, whatever policy you like, have to post the updates on chain, and it has to pass some number of votes on chain. And only if the on-chain environment says that all the things have passed, then the enclave can migrate my data to the new version, and that's how an upgrade would take place. So the remaining problem here is, right now you're kind of subject to the tyranny of the majority. So if you were trusting your sensitive data to this program on the basis that that it's like differential privacy guarantee or whatever, it's good for your privacy, this program, now it seems like you're subject to the will of whatever the developers and the DAO say. Maybe the DAO votes to decrypt all of your privacy, but that's not something that you really wanted to opt into in the first place. What you can do with the trusted hardware, though, is require that not only does this go to a notice period and require a DAO vote, but it can also give users the ability to opt out and reclaim their data. Maybe you're not guaranteed that you can keep using the system because the system's forked and moved on to a new rule set, but you can defend your right to opt out of any changes that would change your privacy policy. This, to my knowledge, is something that no existing systems, even the ones that are close and kind of follow the paradigm that I've mentioned here, don't apply this, but that's the sort of thing that you can require from the trusted hardware to do it. I will stop for questions. I promise I do have slides on caveats so we can talk about all of those. I've glossed over all of the bad things about trusted hardware and just focused on, interesting consequences of the model. I quickly want to shill this upcoming work in progress paper, although I think you just click it and it's work in progress, but it's already there. So I guess tell us what you think of it. But this is all about how to use trusted hardware to do interesting things by encumbering Web 2 accounts. Like you log into an account, but you change the password so that only the trusted hardware has access to it. Now you can impose these delegation or secondary market or other surprising uses, repurposing existing Web 2 accounts for exciting new Web 3 purposes. So this is a work in progress, but you can see some of the discussion there. That's it. Thank you.